Well, so long we were dealing with liquid solutions where both the components or the multi-component mixtures which we were considering, they were miscible with each other over the entire range of composition. Now, when they were miscible, we found that they could exhibit ideal solution behavior, they could also exhibit non-ideal solution behavior. What happens, how to account for those things we have been discussing, and in the end we discussed a very peculiar counterintuitive phenomena, the retrograde condensation, which happens for binary and multi-component liquid solutions. Well, today we will be shifting to a slightly different systems which are not miscible over the entire range of composition. We will be dealing first with partially miscible systems, where the solution or the components, they are miscible over certain ranges of composition and they are immiscible over other range, and then we will try to find out why liquids are miscible under certain conditions, they are not miscible under certain conditions, the phase diagrams for partially miscible systems and also the phase diagrams for completely miscible systems. Now, let us discuss a few salient features of it. First thing is, why are components, rather what happens due to which the components, they do not mix with one another. Now, we have already discussed, when we were discussing the thermodynamic potentials, we have already discussed that under constant temperature pressure conditions, any particular system, it will act such that its Gibbs free energy minimizes in the course of the process, or in other words, mathematically if we put it, we have seen that the condition of thermodynamic equilibrium under conditions of constant temperature and pressure is given by this particular equation. Okay. And therefore, it is quite evident that when there are two components which mix, definitely they will be miscible if after mixing the Gibbs free energy of the solution is less as compared to the Gibbs free energy of the original components. For example, this particular situation is given by curve 2 in this figure. In this particular curve, we find that a single liquid phase will be obtained over the entire range of composition starting from x1 equals to 0 to x1 equals to 1. Now, for such a binary system, we find that Gibbs free energy, it is a function of, as we know, it is a function of temperature, pressure and composition. We have discussed the different relationships, etc. And for the system to be stable, as I have already discussed, dGTP has to be equal to 0. Now, if we consider the dependence of G by RT over composition, just the curve which I have shown in this particular figure. And here we find that, as already discussed, for a completely miscible system, the Gibbs free energy of mixing always reduces, it is always less as compared to the Gibbs free energy of the individual components. Now, under certain conditions, if it happens that on mixing, instead of following curve 2, the solution, rather the mixture, it follows curve 1. That means, in curve 1 we find that over this particular portion starting from x1 equals to 0 to say x1 equals to x1 prime, we find that there is a decrease in the Gibbs free energy change of mixing. Okay. So, over this particular range, we know that the solution, or rather the two components, are miscible with one another. But what about this particular portion which is accompanied by a hump in the curve? In this portion, we find that the system, it can attain the lower value of Gibbs free energy if instead of mixing with one another, they remain as two separate components or two separate liquid solutions whose compositions will be given by x1 prime and x1 double prime. So, naturally we find that the minimum value of G is not given by the solid curve, but by the dotted line which joins the 2 points, say point C and say point D. So, therefore, the system, it can attain the minimum Gibbs free energy if instead of a solution it exists as a mixture of two phases, where the composition of the two phases will be given by x1 prime and x1 double prime respectively. So, therefore, any mixture which has an overall composition in this particular range, it will not remain as a solution, but it will break up into two liquid phases with the compositions as I have mentioned. And therefore, this is dictated by the condition of stability or the condition that the Gibbs free energy of a system has to decrease if a spontaneous reaction has to take place. Now, let us see what will be the vapor liquid equilibrium diagram for such a system. We have already discussed the VLE diagram, the TXY and the PXY diagrams for completely miscible systems, and also the XY diagrams. Let us see what will be the vapor liquid equilibrium diagram under this condition. What is the system that we have here? We have one vapor phase, one liquid phase and another liquid phase. Both the liquid phases, they have some, suppose it is a binary mixture, that means it comprises of two components, then what do we have? In the vapor we will have both the components. In one liquid phase, there will be a predominance of one component and a lower proportion of the other component, and vice versa for the second liquid phase. Or in other words, we have a vapor phase, we have a liquid phase denoted by L1, which primarily comprises of component 1, where component 2 is dissolved in it, and we have another liquid phase 2, which primarily comprises of component 2 and small amount of component 1 dissolved in it, right. So, these are the three phases that we have, unlike the two phase systems that we have been discussing so long. So, therefore, if there are three phases, what is F in this particular case, when we know that for a binary system we know P equals to 2, we know C equals to 2, we know P equals to 3. So, therefore, for all the three phases to coexist, F has to be equal to 1. So, therefore, from here we can conclude that the three phases can coexist under one particular composition, temperature and pressure conditions. Under all other temperature, pressure, composition conditions, either two of the three phases are going to be there, all the three phases cannot coexist. So, let us see what is going to be the phase diagram for such particular systems. We find that for such systems, as I have already mentioned, that since F equals to 1 for the three phases to coexist, so we find that the three phases can coexist only under this particular condition, which is denoted by C, and this is a typical TXY diagram that we have drawn. Since it is a TXY diagram, this is drawn under constant pressure conditions, and the point where the three phases can coexist, that is given by the temperature T star at the constant pressure P. Definitely T star will be different when we deal with different pressure conditions. Now, what do we find here? We find here that the vapor of particular composition is in equilibrium with the liquid L1, whose composition will be given by XD, and a liquid L2 whose composition will be given by XB. Above T star, what do we find? Above T star, we can either have only a vapor phase here, we can have only L1 phase here, L2 phase here, and we can have L1 phase here, or else we can also have a mixture of L1 plus the vapor phase. L1 means predominantly component 1 with a small proportion of component 2 dissolved in it, or we can have L2 and the vapor phase in equilibrium, where L2 is predominantly component 2 with a small proportion of component 1 dissolved in it. So, this is the situation above T star. Below T star, what can we have? Below T star, either we can have one particular liquid solution which is L2, which is predominantly component 2 with small amount of component 1 dissolved, or we can have a single liquid phase L1 which is component 1 with small amount of component 2 dissolved in it, or we can have two separate liquid phases L1 and L2, where L1 comprises predominantly of component 1, L2 comprises predominantly of component 2, and depending upon the overall composition, the compositions of the two liquid phases can be obtained from the horizontal tie line or the intersection of the horizontal tie line with the demarcation boundaries of L2 with L1 plus L2 and L1 with L1 plus L2, right. So, therefore, if the composition is given by say point M, for the composition xm in this particular case, we find that it separates out into L1 and L2, where L1 composition is given by xs and L2 composition is given by xr. Suppose instead of that we find that more or less the overall composition is given by say x p, for example. So, in this particular case what happens? We find that the system it exists as a liquid phase comprising of two liquid solutions, where one solution L1 is given by a composition say this particular composition say x1 prime, and L2 given by a which is denote or rather which has a composition of x2 prime. Now, for this particular same composition, suppose we go for a higher temperature, a temperature higher than T star, say at this particular point. Here what do we have? We have the same overall composition, but we have varied the temperature. We have only a vapor phase, right. From this vapor phase, if we start reducing the temperature, the overall composition remains the same, and we find that the vapor it keeps on cooling till it reaches point 2. At point 2, the first drop of liquid appears or the first dew appears. This is the dew point of the vapor mixture at a temperature T and an overall composition of Xp. The dew which is formed has a composition corresponding to X4, or rather under this condition the dew which is formed it comprises of L1 which has a composition of X4. Now, with the same overall composition, if we continue this cooling process, what are we going to have? We find that it follows the path 1, 2 and 3. Say in due course during the cooling process, the mixture it reaches point 3, where it is separated into a vapor phase of composition Y5 and a liquid phase of composition X6. We can keep on continuing this particular cooling process. We find that on further cooling, the composition of the vapor phase is given by say Y10 and the liquid composition is say given by X10. So, therefore, we find that as we continue this cooling process, the vapor composition travels along GC, while the liquid composition, while there is just one particular liquid which is in equilibrium with this particular vapor, that liquid comprises of predominantly component 1 with small proportion of component 2, and its composition keeps on varying along GD as the cooling process continues, and this continues till we reach the horizontal line given by CD. At this point we find that the vapor phase completely disappears and it separates out into two liquid phases whose compositions are given by XB and XD. A liquid L1 with composition XD and a liquid L2 with composition XB. Now, if we still continue our cooling process, we find that we will be left with two liquids only, and the compositions of the liquids will be varying along the curves ED and AB. Now, this was when we started with a composition of vapor whose overall composition can be given by Y1. Instead of that, if we start rather with a much lower vapor composition, say we start at Y7 and we continue the same particular cooling process at constant pressure. Pressure is kept constant, we continue the cooling process. What happens? The vapor keeps on getting cooled and it follows the paths given by 7, 8, 9, a vertical line in this particular phase diagram, right. Now, in the cooling process, when the vapor reaches points 8, what do we see? We find that the first dew appears. This dew comprises of L2, okay, and the composition of L2 is given by X10. We continue the cooling process. While we continue the cooling process with the overall composition remaining same, we reach say 0.9. Now, under this condition, the vapor composition is given by Y12, while the liquid composition it is given by L11. If we keep on continuing this cooling process further, we find that the vapor composition travels along FC, while it is in equilibrium with a single liquid comprising predominantly of component 2, and its composition varies along FB. And finally, when we touch this horizontal line BC, we find that there is no amount of vapor left, and the system which we are left with comprises of two liquid solutions. One of them, the composition of one of them is given by XB and the composition of the other is given by XD. So, therefore, we find that which particular phase is going to exist, or rather which phases are going to exist under constant pressure conditions, it depends definitely on the temperature, but also on the overall composition of the mixture that we have at hand. For example, suppose we start at some particular point, say F. This is say point 1, right, and we start cooling it. What do we find? We find that as we continue the cooling process, it follows the path say 1, 2, and then it enters the two phase region, and there we have L2 plus V. We continue the cooling region and we enter a single phase a single liquid phase which comprises predominantly of phase 2. So, in this particular case, the TXY behavior is more or less similar to the behavior of TXY that we have studied while dealing with non-ideal and ideal solutions. Same thing is going to happen if we deal with a very high overall composition of component 1. Say we have started with say small a, we start cooling it. We find that initially there is a vapor which is in equilibrium with the liquid phase. Now, this continues and we have a liquid and a vapor region where we find that the composition, as we have already discussed, composition of the vapor phase varies along GC, composition of the liquid phase varies along GD. Now, this continues till we reach point 6. At point 6, the last vapor disappears off and the composition of the last vapor was given by Y5. If we further continue the cooling process, we find that we have not entered the two phase liquid region, rather we have entered the single phase liquid region, or we have entered the region of a single liquid solution. So, therefore, with this we find that it depends whether we are working at a range lower than T star, then we will be having only liquid, where we may have a single liquid phase if the composition lies in this range. We may also have a single liquid phase of a different liquid if the composition lies in this range, or we may have a mixture of two liquids if the composition is given by curves A, B, and the composition lies between the zones of A, B, D and E. If you are working at a temperature higher than T star, then we may either have a single liquid phase, a single vapor phase, we may have a single L2 liquid, we may have a single L1 liquid, or we may have a mixture of L2 and vapor phase, we may have a mixture of L1 plus vapor phase, but only at this particular point we can have the three phases coexisting together. So, therefore, suppose we start with our initial composition at say 13 and we start cooling this particular mixture. What do we find? We find that there is a vapor phase, right. This vapor phase, it keeps on getting cooled, but it remains in the vapor phase and it continues the cooling process. This keeps on happening till we come to the point C. At C, suddenly the entire vapor condenses and forms two liquid phases here. So, therefore, we find that the vapor liquid equilibrium for partially miscible systems comprising of two liquid phases and one vapor phase, it has different zones of coexistence of the liquid and vapor. There is one particular zone of coexistence of vapor and liquid L2, one particular zone of coexistence of vapor and liquid L1, one particular zone of coexistence for L1 plus L2, and just one point of coexistence of the three phases. Now, suppose we have drawn it at one particular pressure. Suppose we would like to repeat the experiments and see what happens if we are drawing this Txy diagram at different pressures. What do we find if we go for higher and higher pressure? There are two things that we observe. First thing is the T star which we have seen, the T star, it keeps on increasing as we increase the pressure, or the three phase equilibrium temperature as it is called, that increases as we increase the pressure. The other thing that we find, we had observed, if you notice the previous slide, if you notice the previous slide, I will just show in the previous slide. If you just notice the previous slide where we had drawn, you will be finding that in this particular case A, B and E, D, they slightly incline towards one another, which shows that the solubility of the phases increases with temperature. As we increase the temperature, greater amount of component 1 gets dissolved in L2 and a greater amount of component 2 gets dissolved in L1. As a result, we find that when we are going for higher and higher pressure, we find that this two curves A, B and D, E, they start inclining towards one another more and more. As a result, the horizontal line which marks the zone of existence of the two liquid phases, that keeps on getting smaller and smaller, till at one particular unique temperature, it reduces to a point which is known as the critical solution temperature. What happens beyond the critical solution temperature? We find that more or less the horizontal portion has disappeared and the Txy diagram resembles the diagram, or rather the phase diagram that we had developed for completely miscible substances with a minimum boiling point, or it resembles the Txy diagram of a minimum boiling azeotrope. Now, in this particular case, since the solubility increases with temperature, we find that there is an upper limit to the range of existence of the horizontal portion, or the upper limit to the range of existence of the two immiscible liquid phases. Accordingly, this is known as the upper critical solution temperature. There are cases where we find that the solubility actually it decreases with pressure. Under that condition, we have a lower critical solution temperature. But let me tell you, that is much less common. A more common phenomena is solutions which exhibit upper critical solution temperature, but we have lower critical solution temperature, or the solutions exhibiting lower critical solution temperature where there is hydrogen bonding. For such cases, there are also certain systems which I have written down where we find that they exhibit both a upper as well as a lower critical solution temperature. So, this diagram it shows the phase stability in 4 binary liquid mixtures which exhibit increase in solubility with temperature, decrease in solubility with temperature, and also exhibit an upper and a lower critical solution temperature. Well, there is one more thing that is quite interesting, and I would like to mention it. The first thing is, so therefore, what do we find? We find that the condition of instability of the binary liquid mixture, it depends on two things. Firstly, it depends upon the non-ideality of the solution, and it also depends upon the temperature. Now, and for the simplest case, we find when GE is given by the one parameter equation, in other words, when G is given by the 2 suffix Margulis equation, for such cases we find that the consolute temperature, this is given by the equation A by 2R. The derivation is pretty simple, but I will not be going into the details of this since there is some constraint of time also. So, therefore, we find that the consolute temperature is given by A by 2R, where the excess Gibbs free energy is given by the 2 suffix Margulis equation. And from this equation it appears that Tc should always be a maximum, but in reality we know that it can be a maximum or a minimum. And although upper consolute solution temperatures are more common, we do have lower consolute solution temperatures in mixtures where components form hydrogen bonds. And we also find that if G is given by this equation, then usually the composition corresponding to Tc is given by x1 equals to x2 equals to half. But usually we find that G is not given by such a symmetric distribution, or G is usually not so very symmetric with x1 and x2, and therefore, the coordinates of the consolute point is often not at the composite midpoint. Well, there is one more interesting thing that I would like to point out, and we will be discussing it in the next class.